Quarter 1 Assessment Review. You can access this video and this review at srhschem.wikispaces.com. The first section is about atomic structure. Question 1 asks us to complete a table about the subatomic particles. So first we have the proton. Protons have a positive charge and they are located within the nucleus. The mass of a proton is going to be relatively large. Neutrons are neutral, and they are also found in the nucleus, and they also have a very large mass. Electrons are negative. They are in an electron cloud that orbits the nucleus, and their mass is much, much smaller than a proton, about 2,000 times smaller. So most of the mass of the atom comes from the protons and the neutrons. So protons and neutrons would be like elephants, and then electrons would be like marbles by comparison. In question 2, we have an atom with atomic number 12, a mass number of 25, and an electron configuration of 1s2, 2s2, 2p6, 3s2. So first, how many neutrons are present? So the mass number of 25 is going to be the sum of protons and neutrons together. And we know because the atomic number is 12 that there are 12 protons. So if we subtract out the 12 protons from the sum of protons and neutrons, we're going to be left with 13 neutrons. Next question asks about the charge of the atom. So the electron configuration shows us 12 electrons. So we have 2 in 1s, 2 in 2s, 6 in 2p, and 2 in 3s. So those 12 electrons match the 12 protons that we have. So 12 protons would give a positive 12 charge, and 12 electrons give a minus 12 charge. So that means overall the charge is 0 or neutral. What element is this atom? So because the atomic number is 12, this is going to be an atom of magnesium. Next, we have to draw the Lewis diagram for the element. So in order to draw the Lewis diagram, we have to identify the number of valence electrons. So this is the ground state electron configuration, and the highest energy level is energy level 3. And there are 2 electrons in that highest energy level. So I'm going to need to go ahead and draw 2 dots around my magnesium. One thing that you can do to help with the placement of the dots, you can draw kind of a tic-tac-toe around the atom, and then on each side you know that you can place one electron, and then you go around and you can place another electron. In this case, we only have 2, so we stop after we place those 2 dots. For the next question, we're going to need to know a little bit about atomic structure and isotope. So first, the atomic number is equal to the number of protons. So you can think AP, atomic number, number of protons. This is always the same for a given element. So magnesium will always be 12 protons. The mass number is the sum of protons and neutrons. So this can change based on the number of neutrons. Charge, you combine your positive protons with your negative electrons. For example, in a neutral carbon atom, there are plus 6 protons, and 6 electrons gives you negative 6, so that gives you 0. Cations will have positive charge, whereas anions are going to have negative charges. When it is neutral, that means that there is no charge. We also write our isotope notation. We use the element symbol, and then we put the mass number on top of the atomic number, and then afterwards we can put the charge. So for example, this is carbon, carbon 12, which has a charge of 0. This is a carbon 13 with charge of 0 and a carbon 14 with charge of 0. So you should note that for all of them, the number on bottom, the atomic number, is 6 because carbon will always have 6 protons. So now we can work to start filling in this table. So let's start with our first one. First, we already know that the atomic number is going to be 35 because we have the symbol. So the number on bottom gives us the atomic number, which is equal to the number of protons. My mass number is 80. I also get that from the symbol. So that means that I must have 45 neutrons because 35 plus 45 would make the mass number of 80. My charge is 0. I also get that from the symbol. So that means that I must have an equal number of protons and electrons. So based on this charge of 0, this particular atom is neutral. For my next one, it looks like I don't have enough information to fill this out, but I really have everything that I need. My atomic number is 30, so I have 30 protons. My number of neutrons has to be 37. The mass number is 67, and 30 of the 67 are protons. So the other 37 must be my neutrons. I know that because the charge is -1, there's got to be one more electron than the number of protons. And since this has a negative charge, this would be an anion. So I can put all of this information together. I have atomic number 30 with mass number 67. I can look at my table of elements and I see that atomic number 30 corresponds to zinc. And this particular zinc has a charge of -1. Next, I have an atomic number of 17, which means that I also have 17 protons. I can add up my 17 protons and my 19 neutrons, and that's going to give me the mass number of 36. As far as the charge, I have an equal number of protons and electrons, so the charge will be 0, which makes this a neutral atom. So atomic number 17 corresponds to chlorine, and my mass number is 36, and the charge is 0. On my next line, I have the protons, which means that the atomic number is 30. I also know that the mass number has to be 66 because I have 30 protons and 36 neutrons. That makes 66 for the mass number. The charge is +1, so I know there must be one less electron than the number of protons. So I need one more proton than the number of electrons. So this would be a cation. I can look this up on my table of elements, and once again I have zinc, but this time this zinc has one less neutron. So the mass number on top is different. Last one in this problem. My number of protons is 28, so my atomic number is 28. Because the mass number is 62, I can just subtract 28 out of 62, and that leaves me with 34 neutrons. If I look at the number of protons and the number of electrons, I have 2 more electrons than protons, so electrons are negative, my charge is -2, making this an anion. If I look at my table of elements, I can find atomic number 28, and that will correspond to nickel. So the next question, which pair of atoms in the chart represents isotopes? So isotopes are going to be atoms of the same element, but they're going to have different number of neutrons. So the atomic number, which is the number of protons, is the same because it's the same element, but the mass number is different because I have a different number of neutrons. So in the table, there was a pair of zinc isotopes. I can tell that these are isotopes because they both have 30 protons. They're both zinc. But because they have different mass numbers, they must have different number of neutrons. So one of these has 37 neutrons and the other has 36 neutrons. In the next question, which would have more electrons? So Fe with a +2 charge or Fe with a +3 charge? So in this chart, I have Fe0, Fe +1, Fe +2, Fe +3. And they all have 26 protons because they're iron. Iron has 26 protons. So in order for the charge to be 0, I must have 26 electrons to match those 26 protons, which means that I've lost no electrons. To have a +1 charge, though, I've got to have one less electron than the number of protons. So Fe +1 has lost 1 electron. Fe +2 would have to have 24 electrons, which means it's lost 2. And then Fe +3 would have to have lost 3 electrons. to be a +3 charge. So based on this, the one that's going to have more electrons is going to be Fe+2. So the more positive it is, that means it's lost more electrons. In the next question, we have a bright line spectra, and we want to determine which elements are present in the mixture. So this is a pretty simple process. All that we need to do is to match the lines in the mixture to the known elements that are above it. So if we look at that, we can see that it matches perfectly for lithium and strontium. So those are going to be the elements that are present in the mixture. If you look at cadmium, you see that those lines are missing in the mixture. So because those lines are missing, there's no cadmium present in the mixture. The next question is related to the energy changes that occur when electrons absorb and emit energy. So how does this relate to the bright line spectra that we just saw? So first, I have an electron that is orbiting the nucleus in energy level 1. So it's orbiting the nucleus, and let's say that this electron was to absorb energy. So now it has jumped up to the second energy level. So this is very energetic. This is unstable. So that electron needs to re-emit that energy in order to get back to stability. So that electron absorbed energy, which made it jump up in energy level to what we call the excited state. To get back to the stable ground state, that electron needs to emit that energy. So the emission occurs during the relaxation. So when that electron relaxes back down to its ground state. So the size of that transition, the size of that jump, if it corresponds to the right amount of energy, it might be on the visible electromagnetic spectrum, in which case we would see a color. So the distance of that jump can match the energies that we see on the bright line spectra. So we get an emission line at specific wavelengths, which corresponds to specific colors. The next section is about nuclear chemistry. So first, we have a table about the nuclear decay particles. So an alpha particle is basically a helium nucleus with 2 protons and 2 neutrons. There's no electrons here, so we just use the symbol for helium because it's 2 protons. The charge on this is going to be +2. A beta particle, in particular an electron, this is going to have a -1 charge because it is an electron. Beta particles are emitted whenever a neutron is converted into a proton. So the ratio of protons and neutrons inside of that nucleus is outside of the band of stability. So the nucleus will undergo decay processes, will undergo changes so that it becomes more stable. And one of the ways it can do that is by emitting a beta particle. Another way would be to emit a positron. So whenever a positron is emitted, a proton is converted into a neutron. So positrons have a charge of +1. In the next question, we're asked about the path of an alpha particle and a beta particle if it was moving through a magnetic field. So in this picture, I have 2 plates, and those plates have been charged. So there's a magnetic field occurring between those 2 plates. So if we take a look at our alpha particles are positive. So our alpha particle is going to be attracted to the negative plate because it has a +2 charge. For a beta particle, so beta particles have a negative charge. So that negative charge is going to be attracted to the positive plate. Next question asks us to compare fission and fusion. So fission involves a heavy nucleus splitting into lighter nuclei. So in this example, we have uranium. The fission is initiated by the bombardment of a neutron. And when that neutron hits that uranium-235, the products that are created, we could have xenon-140 and strontium-94. These are lighter nuclei. In the case of fusion, two light nuclei fuse together to make a heavier nucleus. So this is the nuclear reaction that happens in the sun, where hydrogen atoms are fused together to make helium atoms. So we've taken those lighter hydrogens and made a heavier helium out of them. How are mass and energy related in a nuclear reaction? So during the fusion reaction, some of the nuclear mass is going to be converted into binding energy. That binding energy holds the nucleus together. During a fission reaction, the nucleus is breaking apart, so that binding energy gets released. This is related by the equation E equals mc squared. So what this equation is telling us is that energy and mass are interchangeable. And that's exactly what we see happening during the case of a nuclear reaction. We see that some of the energy or mass can be converted in between. Next question, write the equation that shows the indicated type of nuclear decay. So uranium-235 undergoes alpha decay. So that means that this uranium-235 is going to emit an alpha particle, and then whatever particle is necessary for it to be balanced. So whenever you do a nuclear reaction, you want to make sure that the mass numbers add up on both sides of the arrow. So 4 plus 231 is equivalent to 235, so that's correct. And on bottom, uranium has an atomic number of 92. So the alpha particle has 2 protons. So the particle that's given off must be thorium. And I know it's thorium because that number on bottom has to be 90 so that everything adds up to 92. So I look at my table of elements and I determine what type of element has atomic number 90, and it's thorium. Strontium-94 undergoes beta decay. So we need to know what a beta particle is. So my beta particle is going to be 0, -1 e. We use the symbol e because a beta particle is basically an electron. And the same rules apply. I need my top numbers to add up before and after the arrow. So 0 plus 94 equals 94. And then I need my bottom numbers to add up. So in this case, I want both sides to equal 38. So I have -1, which means I have to have 39 because 39 and -1 makes 38. So I look on my table of elements, atomic number 39 corresponds to yttrium. The half-life of a radioactive element is 6 days. So how much time would be needed for a 60-gram sample of the element to decay until there's only 7.5 grams? So we'll start with our 60 grams and half that. So that gets us to 30. Half that again, it gets us to 15. We want to keep doing this until we get to 7.5. So it took 3 half-lives for that to happen, because we had to half 60 3 times to get to 7.5. So 3 half-lives over 1. I know from the problem that 1 half-life is 6 days, so 3 half-lives is 18 days. How much of a 100-gram sample would be left after 36 days? So we're going to start with 36 days. And I know that 1 half-life is 6 days. So that means that 6 half-lives have passed for this 100-gram sample. So I need to take 100 and half it 6 times. So what I end up with is 1.56 grams of the sample remaining after those 36 days have passed. The fission of uranium-235 and the combustion of carbon compounds found in fossil fuels are both used to generate electricity through power plants. So which of these reactions is going to result in more energy being released? So first, the combustion of fuel, burning of fuel, is a chemical reaction. So the energy that is released comes from breaking and forming chemical bonds. In the case of fission of uranium-235, this nuclear reaction has to do with the binding energy from the nucleus. So the energy released is coming from that binding energy in the nucleus. Nuclear forces are very, very strong. If you think about it, you're trying to push together these positive protons in a really small space, and they have to be very close together. So the nuclear force to hold that together to overcome that repulsion is going to be very, very strong. So nuclear reactions release way more energy than chemical reactions. The next section is about periodic trends. So first, how did Mendeleev organize his periodic table, and what order are the atoms in on the modern periodic table? So Mendeleev was not the first person to try to organize the elements together. He started by organizing the elements based on properties. So, for example, how does it react with oxygen? How does it react with hydrogen? What happens if you add it to water? He gathered all this information and used that to create his table. And when he did this, he noticed that those elements, that their properties repeated, and they repeated in a periodic fashion. So that's where periodic table comes from. In the modern table of elements, everything is in order by increasing atomic number. So when we arrange the elements in this way, we see that the properties repeat in a periodic fashion. Next question, what is the group name for each of the following elements? So we have K, which is potassium. That is going to be an alkaline metal in the first column. Fluorine is a halogen. That's column 17. Strontium is in column 2. Those are the alkaline earth metals. And xenon is column 18, which is our noble gases. Next questions are about periodic trends. So just a couple of terms that we need to be familiar with. Group, family, and column all mean the same thing. And this is easy to remember because they all start with letters at the beginning of the alphabet. Period or series and row, those are all the same thing, and those all start with letters that are at the end of the alphabet. So you can remember that those are the same thing. So for 17, we're going to be looking at explaining some periodic trends. So let's start with atomic radius. As we go down a group, down those columns, each new row corresponds to an additional energy level. So as we go down that group, it's kind of like that atom is having more layers of electrons. As we go across a period, for example, as we go across the second row, all of those atoms are going to have 2 energy levels. But as we go across, the nucleus becomes more positive. So we gain more protons. So the nucleus is becoming more positive, and the attraction between those outer electrons gets stronger. So atomic radius is the center of the nucleus to the edge of the electron cloud. As we go down a group, we're getting more energy levels. So that's more layers of electrons. That radius is going to get larger. As we go across a period, we have the same number of layers, but the nucleus is gaining protons, becoming more positive. So those electrons are going to move in, and the radius will get smaller. Ionization energy. So this is how much energy I need to remove an electron. So the weaker the attraction to the nucleus, the easier it will be to pluck that electron away. So the less ionization energy would be needed to do that. So as I go down a group, I'm getting more energy levels. Those electrons are getting farther and farther away from the nucleus. And each time I add an energy level, those inner electrons are actually blocking the outer electrons from the nucleus. So that attraction gets much weaker. So it's much easier to pluck away an electron in that third energy level than it is in the first energy level. So as we go down a group, the ionization energy required to remove an electron decreases. As we move across the period, the number of energy levels is staying the same. So the amount of shielding, that's the blocking of the nucleus by the inner electrons, is remaining constant. But we are getting more protons. So those protons are going to make the nucleus more positive. The attraction is stronger, which means it's harder to take away one of those electrons. So the ionization energy is increasing. The next trend is electronegativity. So electronegativity is how strongly an atom attracts electrons when it's in a bond. So if I have something like a covalent bond where electrons are being shared, one atom might be more attractive to electrons than the other. So as we go down a group, we're getting more energy levels. So that attraction is getting weaker, which means the electronegativity is going down. As we go across a period, the nucleus is gaining more protons, so it's becoming more positive. So the attraction between the nucleus and the electrons becomes stronger as we go across, so the electronegativity increases. The last trend that we're going to talk about is metallic character. So metals are metals because they lose electrons. So we look at the metallic bonding model with the electron C. All of those atoms give up their electrons. Whenever we form ionic compounds, the metal always forms a cation because it loses electrons. So the easier it is to lose an electron, the more metallic something is. So as I'm going down a group, we're getting more energy levels. The attraction is weaker between the electrons and the nucleus. So it's easier to lose those electrons. It's more metallic. As we go across a period, however, that nucleus is gaining protons. So the nucleus becomes more positive, so the attraction between the electrons and that nucleus becomes stronger. So it's harder to lose those electrons, which means that they are becoming less metallic. This also makes sense because if you look at a periodic table, the nonmetals are all the way over on the right side. So as we move from left to right, we are becoming more non-metallic, more like nonmetals. Next question asks us to compare the properties of metals, nonmetals, and metalloids. So metals have delocalized bonding. So that means the electrons are shared between all atoms. So those electrons are going to be able to easily absorb and re-emit light, making metals shiny. Those electrons also prevent the metal cations from ever touching and repelling each other. What this means is that if you hit a metal with a hammer, the atoms are able to slide past each other. So metals are malleable and ductile. They're also going to be good conductors of heat and electricity. Electricity is just a flow of electrons. In metals, those electrons are already flowing. And because those electrons are flowing around, they're going to be good at conducting heat throughout the material. A nonmetal has a completely localized bond. So those electrons are kept in one place. They're shared between two atoms. So for this reason, they're going to have properties that are exactly the opposite of metals. They're going to be dull. They're going to be brittle, meaning that if you hit them with a hammer, they would shatter. And they would be poor conductors of heat and electricity. Now, metalloids show bonding that's in between localized and delocalized bonding. So because it is in between localized and delocalized, the properties are going to be in between that of metals and nonmetals. So it could have some of each. For example, metalloids are semiconductors, which makes them really useful for computers and technology. They might be brittle, but then also shiny. So they'll share properties of both because they have this bonding structure that's in between localized and delocalized. In question 19, we need to identify metals, nonmetals, and metalloid. So the metals are going to be magnesium and sodium. Nonmetals would be carbon, nitrogen, and oxygen. And metalloids are going to be silicon and germanium. So on the periodic table, there is a staircase that starts with boron, and the things that touch the staircase are going to be my metalloids. To the left of the staircase are going to be my metals, except for hydrogen, and then to the right of the staircase are my nonmetals. Next question, which pair of elements are going to have the most similar properties? So the closer together two elements are, the more alike they will be. Elements that share a column are going to have the same valence shell electron configuration. So they will have very similar chemical properties. So the most similar properties would be fluorine and chlorine, because not only are they right next to each other, but they're also both halogens. They're both in the same column. So they all have valence electrons of 7. So 7 valence electrons means that they're going to all react in ways that allow them to gain one more electron. So chemically, they're going to be very similar. The next section is about bonding. So what determines the chemical properties, the bonding of an atom? So that is based on the sharing or transfer of valence electrons. So the number of electrons in the valence or outermost shell is going to determine the chemical properties of an atom. So for example, fluorine and chlorine have 7 valence electrons. They react chemically in very. The next question asks us to predict what type of bond will form. Will it be ionic, metallic, or covalent? So if we start with element A, we have iron, and element B is oxygen. So element A is a metal, element B is a nonmetal. So whenever we have a metal and a nonmetal, it's going to be ionic. The other case, if we had a polyatomic ion, it could also be ionic. Next, I've got sodium, which is a metal, and magnesium, which is also a metal. So this bond type would be metallic. For the next one, I've got oxygen and oxygen. So a nonmetal and a nonmetal is going to be a covalent bond. For the next couple of questions, we're going to be looking at some naming and formula writing. So you should have a periodic table out, as well as a table of polyatomic ions. Whenever we name molecular compounds or covalent compounds, we're looking for the nonmetals, and we're going to use those prefixes. We change the second nonmetal to end with "ide," so chloride as opposed to chlorine, fluoride as opposed to fluorine, and we never start with mono, so the first element should not have the prefix mono. For ionic bonding, we're looking for a metal and a nonmetal, or there's a polyatomic ion present. We have to check our charges, ensure that the compound is neutral, so we crisscross those charges. For uncertain charges, those transition metals, we kind of have to work backwards to figure out what their charge is, and then we show that with a Roman numeral. And once again, we change that second element, which is going to be the anion, we change that to end with "ide." In the case of acids, we're looking for a formula that begins with hydrogen or a name that ends with the word acid. We need to look at the thing that isn't hydrogen. So if it is something that ends with "ide," we name it as hydroblankic acid. We fill in the blank. If it ends with "ate," we just name it as blankic acid. And if it ends with "ite," we name it as blank us acid. And just like with our ionic compounds, we need to make sure that the charge is neutral. So for question 23, we have some formulas and names to write. So first we need to determine what the bonding type is, because as you just saw, depending on if it's ionic, covalent, or an acid, there are different rules for naming. So let's start with sodium carbonate. So sodium is a metal, and carbonate is a polyatomic ion. Therefore, this is an ionic compound. I know the charge of sodium simply from its position on the periodic table. It's got a charge of +1. Carbonate is a polyatomic ion with a -2 charge. So I need to have 2 sodiums to make +2 to balance out the -2 on carbonate. Carbonate is a polyatomic ion. It's made of 1 carbon and 3 oxygens. So it's 1 unit. So CO3 is just 1 carbonate. My next formula is P4O10. So both phosphorus and oxygen are covalent compounds, which means that we're going to use our prefixes to name these. So the prefix for 4 is tetra, and the prefix for 10 is deca. So this compound is going to be tetraphosphorus decaoxide. Next, I have phosphoric acid. So phosphoric acid, it has the form of blank-ic acid. So this is going to be originally ending with 8. So with phosphoric acid, the name's a little funny, but if we have this phos at the beginning and it ends with 8, that's phosphate. So phosphate is a polyatomic ion, PO4, so 1 phosphorus and 4 oxygens makes 1 phosphate, and that has an overall charge of -3. Since this is an acid, we're going to put hydrogen in front. So my charges are not balanced, so I need 3 hydrogens in order to make +3 to balance out the -3 from phosphate. My next one, I've got iron, which is a metal, and then SO4 is a polyatomic ion. So this is definitely ionic. A big hint for polyatomic ions, if you count more than 2 types of element, then that means you've probably got a polyatomic ion. So Fe is iron, and iron is a transition metal, so it can have many possible charges. So I have to figure that out and indicate it in the name. So to do that, let's start with the SO4. So SO4 has a -2 charge, which means the positive charge to balance that out must be +2. So there's only 1 iron, so the charge of that 1 iron must be +2. So I've got iron 2, SO4 is sulfate. Next I have perchloric acid. So this is definitely an acid, and we also have the form of blank-ic acid. So that perchlor originally ended with 8, so that's perchlorate. So perchlorate is ClO4, and it has a charge of -1. We put in hydrogen in front because it's an acid, and that has a charge of +1. So those charges already balance out. For my next one, I have H2CrO4. So since I have 3 different types of element here, I already know that I've got a polyatomic ion. This also starts with hydrogen, so this is going to be an acid. So in order to name this acid, I need to take a look at the thing that isn't hydrogen. So the name of that is chromate. That's a polyatomic ion. It ends with 8. So if we have an ending of 8, that matches to blank-ic acid. So chromic acid, chrome goes in the blank. That's the name of the formula that we have here. Cobalt-2 bromide. Cobalt-2 is a metal, and that Roman numeral is telling me the charge of the metal, not how many of them are in the formula. So cobalt-2 is going to be a +2 charge. Bromide was originally bromine, which forms an anion with a -1 charge. So those charges don't balance out. I need 2 bromines to make -2 to balance out the +2 from the cobalt. So for our last set here, I'm starting off with copper, phosphorus, and oxygen. So right away, I know that this has 3 different types of elements. So I've probably got a polyatomic ion, making this compound ionic. So in order to name this, we've got Cu, which is copper. Copper is one of our transition metals. So we don't know what charge it is. We have to figure it out. So PO4 is phosphate, and its charge is -3. So the positive charge that I need to balance out the -3 is a +3. Well, there's 3 coppers, so each copper must be +1. So I'm going to name this as copper 1 phosphate. My next compound is copper 3 sulfate. So this is also going to be ionic because we have copper, which is a metal, and sulfate, which is a polyatomic ion. This particular copper is going to be +3. Sulfate is the polyatomic ion SO4 with a -2 charge. Those charges don't balance out, so a quick way that we can do that is just by crisscrossing the charges. So Cu2 SO4 in parentheses with a 3. So I need 2 coppers and 3 sulfates. So a sulfate is SO4. Just like how a car is 4 tires and a body, a sulfate is 4 oxygens and a sulfur. So I need 3 of those to balance out the +6 charge from the 2 coppers. My last compound is an acid because it starts with hydrogen. So I need to look at the thing that isn't hydrogen, which in this case is going to be cyanide. So the way that we name it whenever it ends with "ide" is hydroblankic acid. So cyan goes in the blank. So this is hydrocyanic acid. In the next question, determine if the formula is correct, and if it is not, fix it. So we start out with CaCl. Calcium has a +2 charge, whereas chlorine has a -1 charge. So that can't be the formula because it's not neutral. So the correct formula has to be CaCl2. I need 2 chlorines to make -2 to balance out +2 on calcium. For my next compound, I've got 2 polyatomic ions. I've got ammonium, which has a +1 charge, and nitrate, which has a -1 charge. So ammonium nitrate, that's the correct formula because I have +1 and -1. Hydrogen has a charge of +1, and cyanide, Cn, has a charge of -1. So I shouldn't have 2 hydrogens. I only need 1 to get +1 and -1. For calcium hydroxide, calcium has a charge of +2. Hydroxide has a charge of -1, but there's 2 hydroxides giving us -2. So that formula is correct. Next, I have BaHCO3. So Ba, barium, has a charge of +2. Hydrogen carbonate is a polyatomic ion with a charge of -1. So for this formula to be correct, I actually need 2 of those hydrogen carbonates to make -2. So for the next question, the name and formula pairs are incorrect, so fix them so that they are correct. So first I have calcium bromide. So first thing that's wrong here is that this formula is not correct because calcium has a charge of +2, whereas bromide has a charge of -1. So the name is still okay, but the problem is that the formula should be CaBr2. Next we have FeCl2. So the charge for Cl is -1, and there's 2 of them, which makes the charge of iron +2. The name has it as +3, so the name is not correct, and that should be iron 2 chloride. For my next compound, I've got carbon disulfide. Di means 2, and in my formula, I don't have 2 sulfides. I only have 1. So this should be carbon monosulfide. Next up, I have KNO2, which we have named as potassium nitrate. That's almost correct, except nitrate has a formula of NO3. NO2 is nitrite, so this should be potassium nitrite. Last, I have H2SO4. We have this named as hydrosulfuric acid. This is not correct because we have sulfate. If it ends with 8, it should just be blankic acid, no hydro in front.